So the first two here, right is a sum, right in summation notation, in other words. Now both of these end with the dot saying that this is an infinite series or infinite sequence. So it's going to be from I equals 1 to infinity for both. Now there are two ways we could write this one. This is an arithmetic sequence. We start with 2 and each time it is adding 6. So I can either start with 2 and then add to it, no parentheses, add to it 6 times n minus 1. Or, equivalent to that, would have been I equals 1 to infinity. And I could have done, instead of starting at 2, I could have backed up 6 and did a negative 4 plus 6n. Notice they're equivalent. Just the extra 6 here came from the 2 is now a negative 4, where here I did n minus 1 to get rid of that extra 6 at the beginning. But either one of those describes this sum here. Number 2 is a little tricky. It's not an arithmetic sequence. It's not a geometric sequence. And I didn't write it out explicitly so it was obvious to you. But if you look at each of these, and actually the first term is screwed up so it's not going to work. That first term should have been a 3. I copied it down wrong. Sorry about that. So you probably didn't find one for number 2. But what it should have been was each would have been n squared minus 1. Starting at 2. So probably would have had to, if I started at 1 in my summation, it would have been n plus 1 squared minus 1. So would have been from I equals 1 to infinity of I plus 1 squared minus 1. That's not a possible sum to find, by the way. That one does not converge, so you wouldn't be able to find that infinite sum. But I screwed that up, so there was no way you could possibly have gotten that one right. Number 3, 3 through 5 actually, we're trying to find those sums. One of them is infinite. Number 3 is infinite. We are going from 1 to infinity of 4 times 1/4 to the power of I. Well, this is a geometric sequence. And in a geometric sequence, if we are going for an infinite sum, the formula is that that infinite sum is equal to a1, which is that first term, over 1 minus r, where r is that common ratio. Well, here the first term, 4 times, a1 is going to be 4 times 1/4 to the power of 1, which is just going to be 1. So a1 equals 1. R is the 1/4. That's that common ratio. So 1 minus 1/4. So that's going to be 1 over 3/4. We divide that out. That is 4/3 or 1 1/3, whichever way you prefer to write it, is the infinite sum of that sequence. Now, as far as number 4 is concerned, this is not infinite. This is a finite sum. We go from 1 to 20. So there's 20 terms in it. But it is still geometric. We have 500 times 0.1 to the power of I. So again, we need to find a1. Well, a1 is going to be 500 times 0.1 to the power of 1, which will be 50. So a1 is 50. R is the 0.1. So this sum is going to be 50 over 1 minus 0.1. So that'll be 50 over 0.9. Oops, sorry. This is not an infinite sum. Got to get the right formula. So if we do have a1 equals 50 and r equals 0.1, the formula for a finite sum is that a1 times 1 minus r to the n, where n is, in this case, n will be 20. That's the last term of the sequence, the 20th term, over 1 minus r. So for a finite sum of a geometric sequence, we use that formula. So now let's plug in. A1 is the 50. 1 minus r, so 1 minus 0.1 to the power of 20 over 1 minus 0.1. Now to put this in the calculator, it's a little tricky. We have to add some sets of parentheses. We have to add a set of parentheses in the numerator and a set in the denominator. So to punch this in, I'm going to start off with the parentheses. 50 times another set of parentheses, 1 minus 0.1 to the power of 20. Now in many of your calculators, once you do that power of 20, you've got to arrow out to get out of the power. Close that parentheses. Now we got to close it again, that extra parentheses, to say that we're at the end of the numerator. Then we're going to divide by, in parentheses, the denominator will be 1 minus 0.1. Close the parentheses on the denominator. We get 55.555, or 55 and 5/9 is that sum. So it makes sense. It's going to be 50 plus 5 plus 0.5 plus 0.05. That makes sense. It's going to be right around 55. Number 5 here is a geometric series. Or not geometric, sorry. Arithmetic series. I'm not doing very well with my vocabulary today, am I? Arithmetic sequence. Because each time we're adding 4 to it. So we need to find A1. A1 here is 12 plus 4 times 1, or 16. So that's A1. We also need to find AN. In this case, AN is going to be a to the 45th. So it'll be 12 plus 4 times 45. Well, 4 times 45 is 180, plus 12 is 192. So there is A1 and AN, or A45. And remember, the formula for a finite sum for an arithmetic sequence is that that sum is equal to n over 2 times A1 plus AN. So n is the 45. That's our highest index, 45. So this will be 45 over 2 times 16 plus 192. So if we punch that in, 45 divided by 2 times, make sure you put parentheses around this, 16 plus 192, close the parentheses. 4,680 we get. Is that sum. And that makes sense as well, because we're starting at 12 going up to 192, and there's 45 terms in there. So we're looking at somewhere around just over 100 per term is the average. That's what we're really doing here, is we're finding the average value of a term. We take the smallest term and the largest term and divide it by 2. That's the average value of a single term. Then you're just multiplying by n, which is the number of terms there are. Now the last one here, write 0.45 as a fraction. This is actually an application of, oops, my repeating sign disappeared on me. So there's another one that you would not have been able to get the way we want it to. You would have written that as just 0.45 over 100, or 45 over 100. You would have got 9 over 20. With the repeating sign there, it changes it though. This becomes an infinite series. This can be written as 0.45 plus 0.0045 plus 0.000045, and repeat, so on, as an infinite sum of an infinite sequence. Well, that is the sum from 1 to infinity of 45 times 1/100th to the power of I. So here A1 is 0.45, and I is 1/100th or 0.01, however you want to write it. So that is an infinite series, infinite geometric sequence. So our sum, Sn, is A1, I should say S infinity, is A1 over 1 minus R. So that is 0.45 over 1 minus 0.01. So 0.45 over 0.99. And I'm going to multiply both of those by 100 to move the decimal points, because both have 2 decimal places in them. So that's 45 over 99, and now I have to reduce that fraction. Both of those can be reduced by 9, it looks like. 45 divided by 9 is 5, 99 divided by 9 is 11. So that would have given us 5/11ths had I had the repeating symbol on that for you. Okay, so other than the typos I had writing the problems up, which sorry about that, any questions on those? Okay then, well, let's take a look at our new topic for today. We have 2 new lectures, today and Wednesday. Today is going to be mathematical induction, which ties in with these series. And then Wednesday, we're going to talk about counting principles and some basic concepts of probability, really, is where the counting principles come into play. Then next week, Monday, is a review. I figure there's enough stuff that's been covered this semester. I owe you at least 2 hours of review and recap before we do the final exam. Make sure then that for Wednesday, you are ready for the final exam. For the final exam next week, which is going to be on Wednesday, December 18th. Double check that's the 18th. It is. You may use your notes. And of course your calculator. We're going to try to keep you down to a 3-hour time limit. I'm not going to enforce that, but that's kind of looking through the final test. That was kind of my estimate of what, some people might be done in like an hour, hour and a half. But 3 hours is probably going to be looking at a reasonable time. I tried to keep it into the 2-hour class time, but just really couldn't do it. It is about 75% new material and about 25% cumulative. So 25% from the first 2 units. So we'll just say old material. If that helps you out at all. And again, for this final test, you will have a final test review in my math lab, so that's for extra credit. There's a test review. And I would like that to be done by December 18th. So you'll have that done before the test. Well, you can have it done later that day if you want. But there really isn't a whole lot for new work since Monday is going to be a review. So that should be easier for you to have that done by the test. Not a big crunch there. Okay, so let's start talking about our new material here for today. What we're looking at for today that kind of fits right in with these sequences and series we've been talking about is mathematical induction. And what mathematical induction is it's a way of proving or verifying a formula. Excuse me, fighting off a sneeze. Sorry. So anyway, basically if you're dealing with a sequence or a series or sum, is probably the most obvious application of it, or the easiest to see application of it. But there are other applications of it. And in mathematical induction, what is happening is you are assuming or you're showing it is true for some starting point, some initial point, initial value. So like for some of our formulas for sums of series, we might show that, well, it's true for n equals 1, and then we go from there. So then the second step is you assume it's true for n equals k, and then show that if that is true, if it is true for n equals k, then it must be true for n equals k plus 1. Well, what does that mean? Well, some simple examples that we can come away with. Let's say that we are told that the sum from n equals 1, or I equals 1 to n, I should say, or I equals 1 to infinity, of 5 times I minus 3. Let's say I tell you that that is n times 5n minus 1 over 2. How do I verify that? Well, mathematical induction says I have to show it's true for some initial point. Well, if I want this to be the formula to be true from 1 to infinity or 1 to n, I have to show that that initial point has to be n equals 1. So that initial value is going to be n equals 1. So we're going to show it's true for that. Well, if n equals 1, the only term is 5 times 1 minus 3. 5 times 1 is 5, minus 3 is 2. That would be the only term, that would also be the sum. Well, using this formula then, if n is 1, that is 1 times 5 times 1 minus 1 over 2. Well, 5 times 1 is 5, minus 1 is 4. 1 times 4 is 4, over 2 is 2. So that is true. The sum for I equals 1 of 5i minus 3 is equal to n times 5n minus 1 over 2 for n equals 1. So we showed it was true for that initial value of n equals 1. That's the easy part. The second part is also pretty easy. We're going to assume that for I equals n, that is true. So from I equals 1 to n, that 5i minus 3 is equal to n times 5n minus 1 over 2, which is just restating the formula. Step 3 is where we have to start actually doing the algebra. And here we're going to say, we're going to show now, and what I really should have said here instead of I equals n, I should have said n equals k. So I should have put k in there instead of n. But it's going to be the same formula. So that if we're going up to k, the sum of 5i minus 3 from 1 to k is k times 5k minus 1 over 2. We'll show for n equals k plus 1. Well, the sum from I equals 1 to k plus 1 of 5i minus 3 is equal to the sum from I equals 1 to k of 5i minus 3 plus, now notice that sum is by itself, we're adding to that 5 times k plus 1 minus 3. So all we did there is we separated out that last term, that k plus 1 term, by itself. This is just the summation we had up here in our assumption. We know that that must be equal to, or we assume that it's equal to k times 5k minus 1 over 2. So I can substitute that in for this summation. That's going to be just k times 5k minus 1 over 2. And now we're going to add that to 5k plus 1 minus 3. So to add these, we're going to have to do a little bit of work. I have to get a common denominator. To do that, I'm going to have to multiply that by 2, but I'm going to do some simplification there before I do that. So I've got the 5. I'm going to work with this side here for just a second. 5 times k plus 1 over 3. I'm going to end up multiplying that by 2 to make that a fraction over 2. First, though, I'm going to combine inside here. 5 times k plus 1 is 5k plus 5. Still have the minus 3 in there. 5k plus 5 minus 3 is 5k plus 2. So I've combined everything inside there. Now I can multiply by the 2. 5k times 2 is 10k. 2 times 2 is 4. So that's 10k plus 4 over 2. I still have to add that to this term here. I'm going to do some combining there. I'm going to do, oops, come here. The k times 5k and k times negative 1. So that's 5k squared minus k over 2 plus 10k plus 4 over 2. So when I combine, this is simply 5k squared minus k plus 10k plus 4 all over 2. So now I can combine the two terms in my numerator. 5k squared, there's nothing to combine that with. So that's 5k squared. Negative k and positive 10k is a positive 9k. And then I have my plus 4. And that's all over 2. So that's what I get for that summation by breaking down the sum into a known sum plus that one additional term. Now I still need to work with this side of the equation. K times 5k minus 1 over 2 but I need to substitute in k plus 1 instead of just k. So this is going to be k plus 1 times 5 times k plus 1 minus 1 all over 2. So I have to show that that is equivalent to what we had up here from the summation. So k plus 1, I'm going to distribute the 5 here, so that's 5k plus 5 minus a 1 still. So that's k plus 1 times 5. I put an x there instead of a k. 5k plus 4. We're going to combine the positive 5 and the negative 4. That's going to be over 2. And now let's multiply that out. If we do our FOIL here, k times 5k is 5k squared. K times 4 is a positive 4k. 1 times 5k is 5k. And 1 times 4 is 4. That adds up to 5k squared plus 9k plus 4, and it's still all over 2. Notice that is the same as what we had up here. Now I kind of worked with both sides separately on that one just so you could understand the algebra. But let's take a peek at another example, and this time I'll do them side by side so you can kind of see how the algebra works with both sides of the summation. So what I'm going to give you is I'm going to propose that the sum from I equals 1 to n of 1 over, well, let's do this the easy way. Let's do 3 plus 4 to the I minus 1 squared. Oops, no squared, just 4 to the I minus 1 is equal to n times 2n plus 1. So there's my proposed formula, summation formula. So I have to show for n equals 1. Well, again, for n equals 1, the summation is just going to be that single term. 3 plus 4 times 1 minus 1. I'll go ahead and simplify that. Well, 1 minus 1 is 0. So that's 3 times 4 plus 0, which is 3. So that's what we get on the left side. On the right side, I put 1 in for n. 1 times 2 times 1 plus 1. And then I just do the algebra. 2 times 1 is 2, plus 1 is 3. 1 times 3 is 3. So it is true for n equals 1. We showed that. Then we assume the truth of that formula for n. For n equals k. So we're going from I equals 1 to k of 3 plus 4 times I minus 1 is equal to, and we're putting k in for n now, so it'll be k times 2k minus plus 1. We're assuming that that's true. So then the question is, what if n equals k plus 1? So let's do this again. I'm going to do this parallel, side by side here. This would become the sum from I equals 1 to k plus 1 of 3 plus 4 times I minus 1, and that's it. Over here, this would become k plus 1 instead of k times, instead of 2 times k, it'd be 2 times k plus 1, then plus 1. So let's do the algebra on both sides, showing their equivalent. So on the left side, I'm going to work through this algebra first, just like we did before. I'm going to separate this into I equals 1 to k again, of 3 plus 4 times I minus 1, plus that k plus 1 term is just 3 plus 4 times, instead of I put in k plus 1 minus 1. So it's exactly what I did before, is I removed the k plus 1 term from that summation, so I could get the summation that we assumed up here to be true. So I broke it down into this sum plus an additional term, which is all it is. So that sum is the k times 2k plus 1. And we're going to add to that this term here, which I'm going to do some simplifying here. K plus 1 minus 1 is just k. So that's 3 plus 4k. I'm going to distribute my k here. K times 2k is 2k squared. K times 1 is just k. Plus the 3 plus 4k. Well, we have 2k squared, nothing to combine with that. K plus 4k is 5k plus 3. Now I have to show that I come up with the same thing over on the right side. My summation when I combine it. So the k plus 1 I'm not going to do anything with for now here. But in here I'm going to distribute the 2. So 2 times k plus 1 is 2k plus 2 plus 1. I'm going to add that 1. So this is k plus 1 times 2k plus 3. And now I'm just going to FOIL. K times 2k is 2k squared. k times 3 is 3k. 1 times 2k is 2k. And 1 times 3 is 3. So I combine those, I get 2k squared. Oops, come on now. Oops, we lost a word here. Hopefully it recovers. And it didn't. So before we had our unfortunate collapse of word, we'd had over here 2k squared plus, oh, what did it turn out to be? I don't remember what it was now, but I believe it was 5k plus 3, if I remember correctly. And over here we were foiling that out, the k plus 1 times 2k plus 3. So we had FOILed out, and I'll have to repeat a little bit here. The k times 2k was 2k squared. The k times 3 is a positive 3k. 1 times 2k was 2k, and 1 times 3 was 3. And when we add those up, we get 2k squared plus 5k plus 3. We notice we have the same amount on both sides. So that tells us that does work for k plus 1 if, for n equals k plus 1, if it's true for n equals k. And what this is saying is, since we know it works for n equals 1, and since what we showed is that it must be, if we know it's true for one term, it must be true for the next term, because we said that when it's true for n equals k, then it also implies that it's true for n equals k plus 1. Well, then if it's true for n equals 1, it must be true for n equals 2, which means it must be true for n equals 3, which means it must be true for n equals 4, right on up the line. So once we know it's true for one term, we know it's true for every whole number value of n going up from there. I'm going to have you guys try an example in your notes, and I'm going to give you about 3 minutes to go through it here, and then we'll jump in. And we're going to go from the summation from I equals 1 to n again of 1 over 2 to the power of n is equal to 1 minus 1 over 2 to the power of n. So we're going to have you give that a shot. I'm going to give you, like I said, about 2 or 3 minutes, and then we will go. So again, we need to show that this is true for n equals 1. Well, on the left side, if n equals 1, that's just 1 over 2 to the power of 1, which is just 1/2. On the right side, it's 1 minus 1 over 2 to the power of 1, which is 1 minus 1/2, which is 1/2. So it's true for n equals 1. If we assume it's true for n equals k, then we are saying the summation for I equals 1 to k of 1 over 2 to the I is equal to 1 minus 1 over 2 to the k. So that's assumed. Now we need to show or prove for n equals k plus 1. So on the left side, this side here, that becomes the summation from I equals 1 to k plus 1 of 1 over 2 to the I. On the right side, I'm going to give myself a little more room here. On the right side, that's going to be 1 minus 1 over 2 to the k plus 1. So on the left side here, we're going to separate it again like we always do. So we're going to separate this as the summation from I equals 1 to k of 1 over 2 to the I. Plus the k plus 1 term would just be 1 over 2 to the k plus 1. So from our assumption up here, we know that this is equal to 1 minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Oops, get my extra 2 out of there. So now we have to simplify these to show that it is equal to this here. Well, what we can do is this. 1 over 2 to the k is equivalent to 1 over 2 to the k times 2 in the numerator and denominator. So what happens when I do that? Well, what I get is 1 minus 2 times 1 times 2 is just 2. 2 to the k times 2, well, that is 2 to the k plus 1. And of course, I still have that 1 over 2 to the k plus 1 there. So if I can combine these two terms, a negative, they both have the same denominator. So I can combine numerators. A negative 2 and a positive 1 make a negative 1. So that's 1 minus 1 over 2 to the k plus 1. And if we look all the way up on the right side and bring that down, that is what we had over here. Was 1 minus 1 over 2 to the k plus 1. Any questions there? Well, let's look at an example that might be just a touch more difficult. So we're going from I equals 1 to n of 1 over I plus 1 times I plus 2 is equal to n over 2n plus 4. So again, we have to show for I equals 1. Or sorry, for n equals 1, I should say. Show for n equals 1. So this is 1 over 1 plus 1 and 1 plus 2. That's the only term on the left side. On the right side, this will be 1 over 2 times 1 plus 4. On the left side, this is 1 over 1 plus 1 is 2, 1 plus 2 is 3, 1 over 2 times 3 is 1/6. On the right side, 2 times 1 is 2, plus 4 is 6. That's 1/6. So we have 1/6 on each side. That's showing that it is true for n equals 1. We're going to assume true then for n equals k. So our sum from I equals 1 to k of 1 over I plus 1 times I plus 2 is equal to k over 2k plus 4. So again, that is assumed to be true. Now we need to prove for n equals k plus 1. So we're doing the summation from I equals 1 to k plus 1 of 1 over I plus 1, I plus 2 is equal to, we put k plus 1 in here for k. So k plus 1 over 2 times k plus 1 plus 4. Really doesn't matter which side we start simplifying with. Let's start, we'll just, to be consistent, we'll stay with the left side. And as always, we're going to break that down into the summation of I equals 1 to k, and then plus that kth term in the a sub k. So I equals 1 to k of 1 over I plus 1, I plus 2, plus that k plus 1 term will be 1 over k plus 1 plus 1. We put k plus 1 in for I, and k plus 1 plus 2. This term, we know from our assumption, is equivalent, that sum is equivalent to k over 2k plus 1, or plus 4. plus this term is 1 over, this is k plus 2, and this is k plus 3. Now we have some relatively intense algebra to do here. On the left side, I'm going to factor this denominator. So this is k over, factoring out a 2, that's 2 over k plus 2. The reason I did that is now I notice that there is a k plus 2 in both denominators. So that makes it simpler to find common denominators. This fraction has a k plus 3 in the denominator that this one does not. That means I have to multiply this fraction by k plus 3 in both the numerator and denominator. This fraction here has a 2 in the denominator that this fraction does not. So that means that fraction has to be multiplied by 2 in both the numerator and denominator. So here this is going to be k squared plus 3k. Over, now I'm just going to write this out in long form for now. I may need to combine it later to see if they're equivalent, but for now I'm just going to have 2 times k plus 2 times k plus 3. Over here 1 times 2 is just 2 over 2 times k plus 2 times k plus 3. So now we have the common denominator, we can combine numerators. So that is going to give us k squared plus 3k plus 2 over 2 times k plus 2 times k plus 3. Now let's see what we get on the right side of that summation to see if it's equivalent. So we've got the k plus 1 on top. We're going to distribute the 2 down here to get 2k plus 2 plus 4, which is equivalent to k plus 1 over 2k plus 6. Well, that looks very different right now. Let's bring that down. K plus 1 over 2k plus 6. It looks very different until we factor out the 2. This is equivalent to k plus 1 over 2 times k plus 3. What we notice is we're almost a common denominator there. What we're missing is that k plus 2 factor. So we're going to multiply this by k plus 2 in the numerator and denominator. And if you do the FOIL here, the k plus 1 times the k plus 2, you do get k squared plus 3k plus 2 over 2 times k plus 2 times k plus 3. And now they are equivalent. The alternative, by the way, would have been you could have factored this into k plus 1. Oops, write that a little more clearly. Into k plus 1 times k plus 2. And then you could have canceled out the k plus 2 and you would have had the equivalent fraction as well. So there is going to be a lot of algebra in these, a lot of steps, but they're not nothing new really that you haven't seen. It's just a matter of making sure that the hard part is breaking down that summation into the summation we already assumed to be true plus the additional term like we did up here. Okay, it's actually a minute and a half past our break. We're at 10:22. So let's take our break and we'll come back at 10:30. So as you came back from break, if you got a chance, hopefully you looked at this problem a little bit. Sum from I equals 1 to n of n times n plus 2 is equal to n times n plus 1 times 2n plus 7 over 6. So again, let's show this for n equals 1. So on the left side, that's just 1 times 1 plus 2, which is 1 times 3, which is 3. So that's all we get on the left side. On the right side, this is 1 times 1 plus 1 times 2 times 1 plus 7 over 6. Well, the 1 is just 1. 1 plus 1 is 2. Oops, that's 3 times, not plus. Times 2 times 1 is 2 plus 7 is 9. 1 times 2 times 9 is 18 over 6, which is 3. So it is true for n equals 1. Now we make our big assumption. We assume for n equals k, that for I equals 1 to k, n times n plus 2 is equivalent to n times n plus 1 times 2n plus 7 over 6. And now we're going to prove for n equals k plus 1. So that's saying the summation for I equals 1 to k plus 1 of n times n plus 2 is equal to, on the right side, of course up here we should have substituted in k for n in each of those because it is for k. On the right side, this is going to be k plus 1 now instead of k, times k plus 1 times 2 times k plus 1 plus 7 over 6. So we're going to have a lot of algebra to do in both sides of this. On the left side over here, let's break down our summation. So we'll split it in the summation from I equals 1 to k of n times n plus 2, plus then that k plus 1 term is just going to be k plus 1 times k plus 1 plus 2. So let's work with that. First off, we know that this is equal to k times k plus 1 times 2k plus 7 over 6. That is from what we assumed up here. This here, we're going to do some algebra on it. That's actually, the k plus 1 doesn't change, but we're going to combine here to make that k plus 3. We FOIL this out. I'm just going to do a shortcut. That is 2k squared plus 4k plus 3. Over here, let's FOIL this out. K times, I'm going to FOIL these two. That's going to be 2k squared plus, oh, what is that? 2k plus 7k, 9k plus 7 over 6. I am going to put this over 1 and then multiply both the numerator and denominator by 6 so that we have 6 in the denominator. Over here I have to distribute the k. So this is going to be 2k to the third plus 9k squared plus 7k over 6 plus, here when I multiply by 6, that'll be 12k squared plus 24k plus 18 over 6. So we've got the 2. Now we combine, of course, we're adding, we've got common denominators of 6. So 2k to the third, 9k squared and 12k squared is 21k squared. 7k and 24k is 31k. And then plus the 18, all over 6. So again, a lot of algebra there, a lot of symbol manipulation. Let's see if we get the same thing over on the right side. So first thing I'm going to do is I'm going to combine within each set of parentheses here. So the original k plus 1 here isn't going to change. K plus 1 is k plus 2. Here I've got 2 times k plus 1. Well, that's going to be 2k plus 2. But I still have a plus 7 in there yet, and this is still all over 6. So I'm going to do 2 steps at a time here. First, I'm going to add that 7 there, so that becomes 2k plus 9. And then I'm going to FOIL this out. That becomes k squared plus 3k plus 2. That's just doing k times k times 2, 1 times k, and 1 times 2. All over 6. Now I still have to multiply these two. So that one we are going to have to write out as we multiply. K squared times 2k is 2k to the third. K squared times 9 is 9k squared. 3k times 2k is 6k squared. Three k times 9 is 27k. 2 times 2k is 4k. 2 times 9 is 18. So we combine those, we've got 2k to the third plus 9 and... Did I do something wrong there? See, I missed a k somewhere. Something isn't quite working out right here because I should be getting 21k squared here, and I am currently getting 15k squared. But we'll come back and look at that in just a second. So 27 plus 4k is 31k plus 18. My key looks horrible there. Over 6. So we're off there. We have everything looks the same except for the 21k squared and the 15k squared. So let's look back and see where we made a mistake there. Hopefully it's an obvious one. Oh, here it is right here. I wrote that as, nope, that's right. 2k plus 7, right? Yep. So that is right. So we've got, this is correct. There's k squared, or 2k squared plus 9k plus 7. Let's see, make sure we got this right over here. K squared plus 4k plus 3. Ah, there it is, right there. This should be just 1k squared, not 2k squared. So that would make this 6k squared. 9 and 6 make 15k squared. Okay. So that was a stupid mistake. For some reason I did k times k and I got 2k squared instead of just k squared. So there's our mistake, or my mistake, I should say. That would be 6k squared. So 9k squared and 6k squared make 15k squared. So now in our induction formula, we do have identical formulas on either side using the assumption for n equals k plus that additional term, and then using the formula with just k plus 1 in it, we get the same algebraic result. Okay, I've been a little off this morning. I apologize for that. I'm making some silly mistakes writing things down. So anyway, our next step is we're going to talk about binomial theorem. But before we talk about binomial theorem, we need to jump ahead and talk a little bit about something that's actually something we're going to talk about more on Wednesday in counting principles. But something called a combination. The combination is where our binomial coefficients are going to come from. And what it is, a combination is if we're going to choose a number of items from a group without any order being mattered, any order mattering. So let's say I'm looking at a group of 12 candidates that I have for 2 positions. And we have interviewed and we decided that all are equally qualified, all have done equally well in their interviews and any preliminary testing. All 12 of them would be equally good candidates. So we can just choose 2 of them. Now, both of them are going to do the same job, so it doesn't matter who's chosen first or who's chosen second. Order does not matter. We're just choosing 2 of them. So the symbolism for 12 choose 2, it can be written like this, 12C2. But what we use when we're talking about binomial coefficients is we use this notation. 12 over 2, but notice there's no fraction bar, and it's in parentheses. And that is an abbreviation for a combination, but it's also a binomial coefficient. So what it is it's telling us how many different ways can I choose 2 out of 12 in order to get my 2 positions, with all of the equal between the 2 chosen and all are equal between the 12 that we are choosing from. And it goes back to that factorial notation that we talked about last week. And remember, 3 factorial meant 3 times 2 times 1. We start out with that integer, or that whole number, and we multiply it by every whole number down to 1. So 3 factorial equals 6. So here, 12 over 2, the binomial coefficient 12 choose 2, is 12 factorial over 12 minus 2 factorial. So this is 12 times 11 times 10 times 9 times 8 times all the way down to 1. Well, 12 minus 2 is 10, so this is 10 times 9 times 8 times 7 times all the way down to 1. And what you'll notice here is things cancel out. From 10 on down, it cancels out. This is just 12 times 11, which is 132. So 12 choose 2, or that binomial coefficient of 12 choose 2, gives us 132. So let's do that in a general form. The binomial coefficient of n over r, like that, is defined to be n factorial over n minus r factorial. Now, some things to remember. One factorial is equal to 1. 0 factorial is also equal to 1. So if we want to try to calculate some binomial coefficients, like 8 choose 5, well, that's going to be 8 factorial over 8 minus 5 factorial. So that becomes 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's small enough we can write it all the way out. Remember, 8 minus 5 is 3, so 8 minus 5 factorial is just 3 factorial. So that's 3 times 2 times 1. So the 3 times 2 times 1 cancels out. All we have left here is the 8 times 7 times 6 times 5. Times 4. I forgot the 4 when I said that. So 6,720 is the binomial coefficient of 8 choose 5. Well, what if we did 4 choose 0? Well, that is 4 factorial over 4 minus 0 factorial, which means it's 4 factorial over 4 minus 0 is 4, so 4 factorial. Anything divided by itself is 1, so we don't even have to write out the factorials for those. What if we have 6 choose 4? Well, 6 choose 4 will be 6 factorial over 6 minus 4 factorial. So 6 minus 4 is 2, so that's 2 factorial. So this will be 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is just 2 times 1. So we lose the 2 times 1. So 3 times 4 times 5 times 6, or 5 times 6 times 5 times 4 times 3, what is that, 1260, 360, I believe. Let me double check it. It is 360. So that is our one type of binomial coefficient called a permutated coefficient. So let's talk about the combination one. What's happening here in this permutated one, this is when the order does matter. I presented these in the backwards order that I wanted to. So this is when the order does matter. We use that formula as we saw of nr being n factorial over n minus r factorial. So if it's combination where order does not matter, and we'll clean up the notation again on Wednesday when we talk about these in more detail. Then it's actually a slightly more complicated formula. We add an additional term to it. So in our combination of n choose r, it's n factorial over r factorial times n minus r factorial. So if I look at 8 choose 5 as a combination instead of a permutation, it's 8 factorial over 5 factorial times 8 minus 5 factorial. So in this set, when it's a combination rather than a permutation, or combinated rather than permutated, 8 factorial is 8 times 7 times 6 times 5 times 4, on down the line to 1. Well, 5 factorial is 5 times 4 times 3, on down to 1. So that already cancels out the 5 times 4 times 3. But we also have the 8 minus 5. And of course, 8 minus 5 is 3 factorial. So that'll be 3 times 2 times 1. And we could either multiply this out, or we can do cross-canceling or reducing within our fraction here. I know that 3 times 2 times 1 is 6. I'm just going to cancel out the 6. 8 times 7 is 56. So 8 choose 5, there are 56 ways I can choose 5 items out of 8 if the order doesn't matter. Now the neat thing about the combination is, since the order doesn't matter, it doesn't really matter whether I'm choosing 5 items to keep or if I'm choosing 3 items not to keep. I'm choosing 3 items to throw away, basically. Let me show you what I mean by that. Using the combination, if it's 8 choose 3, well, that's 8 factorial over 3 factorial times 8 minus 3 factorial. And you'll notice 8 minus 3 is 5. So it's still 8 factorial over 3 factorial, 5 factorial. It ends up giving us the exact same combination of numbers. So on bottom, we got 3 times 2 times 1, and 5 times 4 times 3 times 2 times 1. It's still, this term cancels out the 5 through 1. 3 times 2 times 1 is 6, cancels out the 6. It's still 56. So if I look at, let's say I have 16 and I want to choose 14. So that's a 16 factorial over 14 factorial, and 16 minus 14 factorial. Well, I'm just going to start right out with the 16 and the 14, knowing that that 14 factorial cancels out everything from 14 down. So that 16 times 15, everything from 14 down is canceled out. 16 minus 14 is 2, so that's 2 factorial, which is 2 times 1. Now I can cross cancel the 2 and the 16, giving me 1 and 8. 8 times 15 is 120. So that works out to be 120. Now I could have done that on my calculator as well. I could have done 16 and gone to my math menu to get the factorial. So I go over to probability to get factorial. It's number 4 is my factorial. Then I could have divided by, notice I get scientific notation because that's an extremely large number, 14 factorial, and then divide that by the 2 factorial. To get 120. So you are still able to do that if you want to, or what I would recommend more is at least cancel out the 1 term, so the 14 on down. So you've got 16 times 15 over 2 times 1, and then multiply. 16 times 15 is 240, 2 times 1 is 2, and then divide that out. So I'd recommend that at the very least you cancel out the 1 term before you punch it in the calculator. Otherwise you deal with scientific notation, and you deal with a lot of keystrokes on the calculator. So 16 choose 14. So what would 16 choose 2 be? Well, we shouldn't even have to work this out. We know it's going to be 120 because it's 16 factorial over 2 factorial. 16 minus 2 factorial. Well, 16 minus 2 is just 14 factorial. So just like over here, it cancels out everything from 14 down. You've got 16 times 15 over the 2 factorial, which is 2 times 1. Again, that's 240 over 2, or 120. What do we get if we choose 0? If I have 5 choose 0, well, that's 5 factorial over 0 factorial, 5 minus 0 factorial. Well, 5 minus 0 is just 5. So the 5 factorial and the 5 factorial cancel out. So I've got 1, and on bottom I've got 1. Well, what is 0 factorial? Well, remember I did that reminder at the beginning. 0 factorial is just 1. So that is a 1. 1 divided by 1 times 1 is also 1. 1 divided by 1 is 1. Well, what if I went to the other extreme? 5 choose 5. Well, that is 5 factorial over 5 factorial, 5 minus 5 factorial. Then you can see what we end up getting there. 5 minus 5 is 0 factorial. It's exactly the same as we had up here. 5 factorial over 0 factorial and 5 factorial. Still comes out to be 1. There's only one way you can take the whole group, or there's only one way that you can take nobody. So now let's bring these back to our binomial expansions. We have done problems like this, x plus 3 to the power of 3. And that gets to be quite a bit of work. You have to pair it up. Where you do the two of them first. X plus 3 times x plus 3 is x squared plus 6x plus 9. And then you have to multiply by the additional x plus 3. I can get my pen to work. There we go. So x squared times x is x to the third. X squared times 3 is 3x squared. 6x times x is 6x squared. 6x times 3 is 18x. 9 times x is 9x, and 9 times 3 is 27. So we've got x to the third plus 9x squared plus 27x plus 27. So there is our expansion of x plus 3 to the third. But that's quite a bit of work in itself. If we got up to be the fourth or fifth or, heaven forbid, sixth power, that's a lot of multiplying out. That's a lot of times of using that adapted FOIL method to multiply those. So what the binomial theorem tells us is that there's a shortcut for expanding this. It says if I have a plus b to the power of n, my first term is going to have a coefficient, a combination coefficient of n choose 0 times a to the power of n, b to the power of 0. My next term has a coefficient of n over 1 times a to the power of n minus 1, b to the power of 1. Now you'll notice these powers here, n minus 1 and n, are always going to add up to n. The next term of the expansion would be n choose 2, again combination, of a to the n minus 2 and b to the second. And this will continue until you get to n choose n minus 1, a to the power of 1, b to the power of n minus 1. Also, you'll notice the bottom term in our combination is always the power of b. And the last term would be n choose n. Of course, we know that's 1 of a to the 0, b to the n. So let's take a look at that. First of all, you'll notice if whatever n is, there are going to be n plus 1 terms in that expansion. So if that's to the power of 7, or there's going to be 8 terms in that expansion. I'm going to try to avoid the power of 7 for right now. But here's what we're going to do. We are going to do x plus 3. Well, let's go to the power of 5. So our first term is going to be 5 times 0 of x to the power of 5 times 3 to the power of 0. Second term, 5 choose 1 of x to the power 5 minus 1, which is just 4, and 3 to the power of 1. Plus 5 choose 2 of x to the power of 5 minus 2 and 3 to the power of 2. Plus 5 choose 3 of x to the power of 5 minus 3 times 3 to the power of 3. And 5 choose 4 x to the power of 5 minus 4, 3 to the power of 4. And the final term, the sixth term, 5 choose 5 of x to the 5 minus 5 and 3 to the 5. So let's figure out these terms. This first term here, 5 choose 0 is going to be 1. 3 to the 0 is also 1. So that first term is just x to the 5th. Plus 5 over 1, that's going to be 5. X to the 5 minus 1, that's x to the 4th. 3 to the 1 is 3. So 5 times 3, that's going to be 15 x to the 4th. 5 choose 2. Well, that'll be 5 factorial over 2 factorial, 5 minus 2 factorial. So 5 choose 2. You notice 5 minus 2 is 3, so 3 on down cancels out. So that's 5 times 4 over 2. Let me write that off to the side here. I just put it over here. 5 factorial over 2 factorial. 5 minus 2 is 3 factorial. Well, the 5 times 4, the 3 on down is canceled out by the 3, divided by 2 times 1. Well, the 2 and the 4, 5 times 4 is 20, 2 times 1 is 2, 20 divided by 2 is 10. So that's going to be a 10. X to the 5 minus 2, that's x to the third, and 3 squared is 9. So 10 times 9 is 90, x to the third, plus 5 choose 3. Well, 5 choose 3 is going to be 5 factorial over 3 factorial, 5 minus 3 factorial. Well, that's going to be 5 factorial over 3 factorial, 2 factorial, just like we had here. So that's also going to equal 10. X to the 5 minus 3, well, 5 minus 3 is 2, so that's x squared. 3 to the third is 27. So 10 times 27 is 270, x squared. Next, we have 5 to the 4, 5 choose 4. Well, that's 5 factorial over 4 factorial, 5 minus 4 factorial, which ends up being 5. So that's 5 times x to the 5 minus 4. Well, 5 minus 4 is 1, so that's just x. 3 to the fourth is 81. So I've got 5 times 81 is, what's that, 405? It is 405. So that's plus 405x. And then finally we have 5 choose 5, which is 1. There's only one way to do that. 5 minus 5, that's x to the 0. So that actually doesn't need to be shown. 3 to the fifth is 243. So that's just simply 243 for that last term. So we expanded that out without having to do that repeated multiplication to get x plus 3 to the fifth. Now, of course, it doesn't stay quite that simple. We can have coefficients on the x, and we can have negatives in there. We could have other variables if we wanted to. So let's do this one here. Let's do 2x minus 5. And let's just do this to the power of 4. Now it's to the power of 4, which means there's going to be 5 terms in this expansion. Our first one is 4 to the 0. Now it's not x anymore, it's 2x to the power of 4. Times, it's not 5, it's a negative 5 to the power of 0. Plus 4 choose 1. So now it's 2x to the power of 4 minus 1. And negative 5 to the power of 1. Plus 4 choose 2. Again, it's 2x to the power of 4 minus 2. And negative 5 to the power of 2. Plus, we've got the 4 choose 3. 2x to the power of 4 minus 3. And negative 5 to the power of 3. And finally, we got 4 choose 4. 2x to the power of 4 minus 4. And negative 5 to the power of 4. So as we expand each of these out, here, of course, 4 choose 0 is going to be 1. 2x to the fourth. Well, 2 to the fourth is 16. X to the fourth is x to the fourth. Negative 5 to the 0, anything to the power of 0 is 1. So that comes out to just be 16 x to the fourth. My next term here. 4 choose 1, that's just 4. 2x to the power of 4 minus 1 is 3. So 2 to the third is 8. X to the third is just x to the third. Negative 5 to the 1 is negative 5. So I've got 4 times 8 is 32 times negative 5 is a negative 160. And then I have x to the third there. Well, 4 choose 2. That's 4 factorial over 2 factorial, 4 minus 2 factorial. Well, 4 factorial and the 2 factorial cancel out, giving us just 4 times 3 over, well, 4 minus 2 is also 2 factorial, so 2 times 1. 4 times 3 is 12 over 2, so that's just 6 for 4 choose 2. 2x to the power of 4 minus 2. Well, 4 minus 2 is 2. So 2 squared is 4. X squared is just x squared. Negative 5 squared is a positive 25. Remember, when you square a negative or a negative to any even power, it's a positive number. So 6 times 4 is 25, times 25 is 600 x squared. And then here, 4 choose 3, that's just 4. 4 minus 3 is 1, so 2 to the 1 is just 2. X to the 1 is just x. Negative 5 to the third is a negative 125. So 4 times 2 is 8, times negative 125 is a negative 1,000. And that's just x is my only variable there. Well, 4 choose 4 is 1. 4 minus 4 is 0, so 2x to the power of 0 is just 1, so there's nothing really to do with that. Negative 5 to the power of 4 is a positive 625. So that last term is simply a positive 625. And there's our binomial expansion of that. One of the powers of this binomial expansion, this binomial theorem, is in many cases we don't care about all of the terms, the whole thing. We just care about one term in that expansion. So we might have a really ugly expansion like, oh, I don't know, 3x minus 2y to the power of, let's go to the power of 12. So that would have 13 terms in it. I don't feel like doing 13 terms, so we're not going to do that. But let's say we're just asked to find the 5th term. Now when we look at these, if we go back up here, the first term, this was 0. Second term, it was 1. Third term, it was 2. Fourth term, it was 3. Fifth term, it was 4. So what's on bottom is always one behind what's on top. So for the it's always behind the number of term it is. So if it's the 5th term, that bottom number is going to be 4. This is the power of 12, so the top number is going to be 12. So our 5th term is 12 choose 4. And then it's going to be the first term, 3x to the power of 12 minus 4. And then the negative 2y to the power of 4. All we have to do is expand this out. Well, 12 choose 4 is 12 factorial over 4 factorial, 12 minus 4 factorial. Well, 12 minus 4 is 8, so that's 8 factorial. So I'll only have to write out the 12 down to 9. So 12 times 11 times 10 times 9. Everything down below there is canceled out by the 8 factorial. This will be over 4 times 3 times 2 times 1. Now I could just multiply this out, but I see that 4 times 3 is 12, so that cancels out. I can cancel out the 2 and the 10, make that 1 and 5. So now we've got 11 times 9 times 5 is, what, 495, I believe? It is. So we got 495 as that coefficient. Or is for the binomial coefficient, I should say. So that is from the 12 choose 4. 3 to the power of 12 minus 4 is 8. 3 to the 8th is going to get kind of large. 6,561. 12x to the 8th is just x to the 8th. Negative 2 to the 4th. Well, it's an even power, so it's going to be positive. Negative 2 to the 4th is actually 16. And then y to the 4th. So I do have to multiply here 495 times 6,561 times 16. So we get 51,963,120. So that's our coefficient. X to the 8th, y to the 4th. Now you can see the numerical coefficient there gets large rather quickly, even with such small numbers as 3 and 2 there. So I'm going to have you find the fourth term of x minus 2y to the 8th. I'll give you a couple minutes, then we'll go over that. So for our 8th term, for our 4th term, this is going to be 8 over 3. Remember that bottom number always trails the term by 1. Then this is going to be the power of x to the power of 8 minus 3, and then negative 2y to the power of 3. So I do the 8, choose 3 first. That's 8 factorial over 3 factorial, 8 minus 3 factorial. Again, we'll start out doing 8 minus 3 is 5, so that's 5 factorial. So this is 8 times 7 times 6, and the 5 and below cancel out with the 5 factorial. We have 3 times 2 times 1. And if we wanted to, we could notice that 3 times 2 is 6, so we can cancel out the 6. That's just 8 times 7 is 56 for that coefficient. 8 minus 3 is 5, so that's going to be just x to the 5th. Negative 2y to the 3rd. Well, negative 2 to the 3rd is negative 8, and then y to the 3rd. So we've got 56 times negative 8, which should be a negative 448. It is. X to the 5th, y to the 3rd. There is our 4th term of that expansion. Okay, it is that time, so remember, we do have old homework from Wednesday that is due tomorrow, due Tuesday. There is also a new quiz due because of the change in schedule over Thanksgiving. The quizzes aren't due on Friday anymore. Those will be due Wednesday. And then, of course, the new homework from today, which will be due Thursday. So again, only one more lecture on new material left this Wednesday. Then next Monday is review, and then we're almost there. On the 18th is our final exam. Anybody have any questions? Okay, well, you guys have a great day, and we'll see you all on Wednesday.